Hello everyone, and welcome to our second web seminar of the series of the Latin American webinars of physics. My name is Germán Arturo Gómez from Catholic University in Chile, and I will be your host today. Our speaker today is Nicolas Bernal from ICTP-SAIFR in Sao Paulo, who will talk about WIMP and SIMP dark matter from spontaneous breaking of a global group. Nicolas received his PhD from Paris 6. After postdoc in Barcelona, Lisbon, and Bonn, he moved to ICTP in Brazil, where he is currently postdoc working on dark matter phenomenology. Nicolas' talk today is titled WIMP and SIMP dark matter from the spontaneous breaking of a global group. We are glad to have him, our speaker today, and we remind you that you can part of the discussion, written questions and comments using Google Plus and Q&A system on Twitter with the hashtag LOWOP. I will now hand you with Nicolas.
Thank you very much, Germán. So let me start sharing my screen. So can you see the slides?
Yes, we can.
Should be okay. Super. Great. So as Germán just said, I will talk about the WIMP and SIMP dark matter from a spontaneous breaking of a global group. So this is a paper that was posted in the archives like a month ago, so you can see here the reference. It has been done in collaboration with Camilo Garcia Celi, who is a postdoc in Brussels, and Rogerio Rosenfeld from here, also from ICTP-SAIFR. So let me start just with saying that even if I talk more about WIMPs and SIMPs, I will focus more on the SIMPs, just because I think it's more interesting, and maybe you're less familiar to the SIMP dark matter, so the strongly interacting massive particles. So just a few comments about the evidence of dark matter, because maybe you're already very familiar too. So there are several observations that indicate the existence of this non-luminous matter, this dark matter. Actually, it's a missing force. It's a gravitational missing force. And this evidence comes at very different scales. For example, scales of galaxies with the flat behavior of the galactic rotation curves, but also levels of clusters of galaxies, for example, with the bullet cluster, this famous picture of the bullet cluster. And also very big scales, for example, the cosmological scales of the level of the CMB anisotropy that can be very good explained in the mode of lambda CDM. So in this, here we'll focus on the scalar dark matter. So, and the motivation is like the recent discovery of this first scalar in the standard model, the Higgs boson. So for me, it's natural to consider extended scalar sectors, right? So we suppose that it exists the standard model, right? And a new sector is a dark sector composed uniquely by scalars, right? And there's a discrete symmetry that protects the dark. It protects the lightest particles of the dark sector. It decays, right? Now, there have been a lot of studies about scalar dark matter, starting from the minimal model. So say you have the standard model, and you enlarge it with a singlet, or a doublet, or doublet and His, singlet, triplets. I mean, there have been a lot of studies since, say, 20, 30 years on that. But there's another possibility, is to go beyond the Z2 symmetry, because usually we impose a Z2 in order to have a stable dark matter. For example, it's in the R parity in supersymmetry, or the K parity in Kaluza-Klein theories. So that's what we will explore. We'll try to go beyond the paradigm of a Z2 parity. So as I told you, usually stability of dark matter means Z2, a Z2 imposed by hand. But that's not the only option. But we could, for example, we can have a Z3, for example, or any Zn. And if we start with this, the dark matter phenomenology will be modified in a substantial way. So another thing is that this Zn, so Z2, Z3, whatever, could be imposed at initial, for example, with the R parity, or it could arise as a remnant of broken global symmetry. And that's the idea what we will take. So we'll assume that we have a global U1 symmetry, which is spontaneously broken by a scalar field of charge 3, and this will generate naturally a discrete Z3 after the symmetry breaking of this global U1. So it has been shown that the spontaneous breaking of a global continuous symmetry, well, as maybe you know, gives rise to a massless Goldstone boson, right? And this could be a problem, or this could be also a candidate for dark radiation, this massless degree of freedom, right? And this has been pointed out by Weinberg, say 2 years ago. So you can use this Goldstone as a candidate for dark radiation. So now let's go to the model. So we'll assume that we have the standard model plus 2 complex scalar fields, which are both singlet under the standard model and under the global U1. So for the scalars, we have X will be a dark matter. H, capital H, is the usual Higgs doublet. And we have an extra, if you want, singlet, a Higgs singlet, which is responsible for the breaking of the U1 down to a Z3. Right? So this is the scalar content of the model. So having this in mind, the most general renormalizable potential is this one. So these first 2 terms correspond exactly to the Higgs mechanism. So you can recognize the mass and the quartic coupling for the Higgs doublet. We have an extra, if you want, Higgs singlet, which has exactly the same structure. So a mass term and a quartic coupling. And this part corresponds to the dark matter, right? A mass, again, and a quartic coupling. Here we have a plus because we don't want to break, we don't want the dark matter, the X, to have to develop a VEV, a vacuum expectation value. So these are, we also have the mixing term. So if, for instance, the Higgs doublet and the Higgs singlet could mix via this coupling lambda phi h, which will be trade for a mixing angle. So later on, you will not see this coupling, but a mixing angle theta. And we have 2 dark matter portals. So this one is exactly a Higgs portal, so dark matter coupling to the Higgs doublet, so the standard model one. And this is a second portal which couples the dark matter and the phi, so the Higgs singlet, right? And because of the choose of the assignation of the charges, we can have this kind of term, which is typical from Z3s. So it couples 3 dark matter particles with 1 phi, with 1 Higgs singlet. So and of course the Hermitian conjugate of this term. So that's the potential that we'll take into account. So the Higgs doublet, Higgs singlet, and the dark matter, plus the mixing angle. So if you want the mixing between the 2 Higgses, so the doublet and the singlet, and 2 portals, right? And this lambda 3, which is the trilinear coupling. So now, of course, as I told you, H is, if you want, is very close to the standard model Higgs, right? So we will develop a VEV of 246 GeV, and we have a singlet, which is written in this way, and the dark matter. So we can choose a vacuum that breaks the SU2 cross the U1 hypercharge, cross the dark U1, down to the U1, the electroweak, so the electromagnetic U1, times the Z3. And when having this, the Z3 is responsible for the stabilization of the scalar dark matter. So these 2 states will have exactly the same quantum number, so they will mix, and the mixing angle is theta. So if you want, is the previous lambda h phi. So one of these states, so it will correspond to it will be the standard model like Higgs, so having a mass of 125. And we have a second one, which is called rho, which mass will be a free parameter, and the dark matter mass. And of course, we have the vacuum expectation value of this singlet, right? The eta correspond to a Goldstone boson, so a massless state that arise from the spontaneous breaking of the global U1. Now, what are the constraints of the model? So first, we have to take care of the effective number of neutrino species, basically because we have a massless state that could fade a neutrino. So in order to have control on that, we have to compute what's the coupling temperature of this Goldstone boson in order not to spoil the measured number of effective neutrinos. So this effective number of neutrinos has been measured and has been recently measured by the Planck collaboration. And this, even if this number is not exactly 3, is incompatible with 3. So it's slightly larger than 3. And 3 corresponds to the standard model neutrinos on the standard model. Right? So we have to make sure that this Goldstone boson will not increase this effective number of neutrino species. So in order to do that, we have to decouple. What we have to do is to compute when the Goldstone boson is decoupling from the thermal bath, in particular from the muons. So we have to do is to compute all the reactions, so the freeze out of all the reaction, the annihilation of the Goldstone boson into standard models, and also the elastic scattering reactions. So we have done that, and here I can show you a plot of the mixing angle as a function of the mass of the rho for different values of this quartic coupling, just to have you to give you an idea. So all these points here inside these curves are in conflict with the Planck measurements. So what we want to do is to be somewhere here, corresponding a small mixing angle and a large value of the rho scalar. So if having that, we can avoid the constraint from dark radiation. So that's one constraint. But we also have to take care of the invisible Higgs decay, because after all, we have a slightly modified Higgs sector. Now the total Higgs width will correspond to the standard model 1 times the mixing angle. But there are also new channels. For example, Higgs can decay into a couple of dark matter particles, or a couple of etas, so Goldstone bosons, and a couple of rhos, right? And the visible Higgs decay will correspond to the decay in dark matter particles, but also in Goldstone bosons. And there's also when Higgs decays into rhos, and subsequently rho decays into Goldstone bosons or dark matter. So this branching ratio of the visible decay of the Higgs has been measured. Sorry, I forgot to say that we also have the Higgs decay in 3 bodies, right, given by these 2 processes at 3 levels. So this has been measured, and this invisible branching ratio has to be smaller than, say, 20%, 20% or so. We're also taking care of the total Higgs decay width, but I mean, typically are the same order, the constraints. So we're taking all this into account, and here I show you the region excluded. So these solid lines correspond to the previous bond that I showed you. So solid lines correspond to dark radiations. However, this dashed line corresponds to the Higgs. So we want to be outside the solid lines for not being in concentration with N effective, but also below the dashed lines, right, in order to avoid Higgs decay, invisible Higgs decay. So for example, we choose this point, this smiley face, corresponding to a small mixing angle of, say, 10 to the minus 5, and a mass of the rho of, say, a few GeVs. So doing this, we can avoid these 2 constraints. But there are other constraints, in particular dark matter direct detection. And as we have an exchange, a scalar exchange of a Higgs and a rho, we'll have a spin-independent signal that could be produced. And we are, of course, taking care of this. And in future plots, I will show you what the constraints look like. And for this, we're taking the result from the LUX collaboration. Now, what about the relic abundance? And here I will first talk very briefly about WIMP dark matter. So WIMPs are these weakly interacting massive particles, and I think we are very used to this because it's the common mechanism used. So a couple of dark matter particles will annihilate in the early universe into a couple of standard model particles. So this is a usual Boltzmann equation, and this is exactly the WIMP miracle that for sure you guys are very familiar to. So the early universe dark matter is in equilibrium, so this solid line, black line, corresponds to the equilibrium density, and at some point the expansion rates is much important than the interaction rates, and as dark matter is stable, dark matter will submit a freeze out. And the typical cross-section that I have in mind is few times 10 to the minus 26 cubic centimeter per second. This is exactly the WIMP miracle. So in order to do that, we have to take care of all this process. So annihilation of dark matter particles into fermions, into vector bosons, but also into Goldstone bosons, so these etas, and this rho or the Higgses, right? So here I'm just showing you what the phase space, the parameter space look like. So we can have the correct relic abundance just with the WIMP miracle. So having masses of the electroweak scale, so say dozens or hundreds of GeVs, and couplings of the order of 1, say 10 to the minus 1, 10 to the minus 2. So for example, here you can see the Higgs funnel, or here the opening of the kinematic openings of the annihilation into Higgses or Ws or Zs. So this is exactly the WIMP miracle with self-annihilating dark matter. But in this model, we have Z3 symmetry, not a Z2. So there's not the only option for achieving the relic abundance. For instance, we can have what is called the semi-annihilation. So semi-annihilation is just a little bit different. So we can have an annihilation, so a collision of two dark matter particles that give rise to one dark matter particle and one standard model particle. So remember that in self-annihilation, you have a annihilation of two dark matter particles into two standard model particles, or at least two non-dark matter particles. Whereas here in the semi-annihilation, we have a couple of dark matter particles that annihilate into one dark matter particle and one standard model particle. So that means that there's a new term in the Boltzmann equation that we have to take into account, proportional to this thermal average cross-section times velocity times n squared, because after all we have the annihilation of two dark matter particles that produces n, so one dark matter particle and one particle which is supposed to be in equilibrium, so one standard model particle. Here I'm showing you in this plot the evolution of the dark matter. So y corresponds to the number, to the comoving number of dark matter particles as a function of x, and x here is basically the inverse of the temperature. So if you want, it goes with the time. So and again, the black line corresponds to the equilibrium density, the red line corresponds to the self-annihilation, and the blue to the semi-annihilation. So here I just want to give you a feeling that even if it's a different process, semi-annihilation compared to self-annihilation, the Boltzmann equation, the solution of the Boltzmann equation is basically the same. So we have all that we know about the WIMP miracle stays for the semi-annihilation compared to the self-annihilation. So it's basically the same mechanism. Now, these are the processes that we have to take into account. So annihilation into one dark matter particle and basically Higgs or a rho or an eta via the contact interaction or via a T channel or also via an exchange of a dark matter in the S channel, right? Okay, there's a, okay, for direct and indirect detection, if the semi-annihilation, so if this term is a dominant one, we'll have a very suppressed direct detection, right? Because these kind of diagrams will not contribute to the direct detection. And from the indirect detection, for example, for gammas or neutrinos, whatever, we'll have also a different, slightly modified features. For example, the spectral endpoint will not be exactly at the mass of the WIMP, but it will be a function of the masses of the final state. So in particular, the mass of the dark matter, but also the mass of the Higgs, the rho, or the eta. So we have a different spectral endpoint, which is interesting for indirect detection. And also we have the flux will be decreased by a factor of 2, just because we are producing only one standard model particle and not two, as compared to the self-interacting, self-annihilating, case. And here I'm showing you just a plot of the parameter space, again, the mass and the coupling that we have to have. Here the principal, the important coupling is lambda 3, because after all is the coupling which mediates the interaction between three dark matter particles. So again, as I told you, all that we know about the WIMP miracle state here, so masses of the order of 2 GeVs, dozens GeVs, hundreds GeVs, and coupling of the order 1, 1, 2, whatever. So that was all they wanted to tell you about WIMP dark matter. Basically, because it's what we know from the WIMP miracle. So as I told, that's not the only post option. We can also have, instead of weak interacting massive particle, we can have SIMP dark matter, and SIMP, the S stands for strongly interacting massive particles. And I will extract more. I will give you more details about that in the next slides. So this mechanism has been pointed out like 20 years ago, but it has been like I think it was kind of forget till say a year ago with this group. So in February last year, so Rivao give a new breath to this 3-2 dark matter annihilation. So the idea is that basically on top of the self-annihilation and the semi-annihilation, you can have mechanism annihilation that only involves dark matter particles. And in particular, you can have this mechanism where 3 dark matter particles annihilate into dark matter particles. So here the standard model at this level is playing no roles whatsoever. And in principle, the two sectors, so the dark matter or the dark sector, could be completely decoupled from the standard model. So what do we need in order to make this mechanism viable, or in order to have this mechanism as the dominant one? So first, look, so just a very, very heuristic level, if we have these 3 terms in the Boltzmann equation, this one has to be the dominant, of course, if we want this to be the leading term. So this, if you want this interaction rate, the 3-2, has to be much bigger than the rate corresponding to the semi-annihilation and the rate corresponding to the self-annihilation. Oops, sorry, here's a typo. It should be self and semi-annihilation. So this could be achieved if you say, okay, there's a visible sector, so the standard model, and the dark sector, which is completely decoupled, or almost secluded dark sector. So they are kind of decoupled. So this is one option, right? But we have to see that this is when we have the 3-2 annihilation, we are going from cold dark matter, so these guys could be cold, to hot dark matter, because of course we are trading mass, so dark matter mass, into dark matter kinetic energy. So these 3-2 annihilations will pump heat into the dark sector, which, I mean, this has been studied. For example, here I'm showing you a plot from 92 where these guys study the 3-2 annihilation. So here's just the evolution of the temperatures of the dark matter temperature and the standard model temperature as a function, if you want, of the time or of the temperature of the plasma, of the photons. So the point is that in the early universe, we have both the 3-2 and the 2-3 reactions in equilibrium. So we are not heating up dark matter, because if you want, this reaction is cooling up, is heating up, whereas this reaction 2-3 is cooling down the plasma. So basically, the evolution of the dark matter temperature is the same as the evolution of the photons. However, when dark matter becomes non-relativistic, only the 3-2 process are kinematically allowed, and we're reheating the dark matter temperature. So we've got an increase of the dark matter temperature with respect to the standard model sector. And then at what moment, say at T around 20 or so, times the dark matter mass, we have the dark matter freeze out, and then dark matter will decrease its temperature as 1 over the scale factor square. Okay, it's details. Okay, this is one fact. The point is that this is ruled out by structure formation. We cannot let dark matter to heat up that much. So in 95, these guys point out that this is excluded. Okay, so what we need is we have to avoid this dangerous increase of temperature of the dark matter. So in order to have that, we have to have a kinetic equilibrium at least until the freeze out. And kinetic equilibrium basically means that the temperature of the standard model is the same temperature of the dark matter. So we have to avoid dark matter to heat up. So again, okay, now what process we have to compute we want for the 3-2? So basically we have to compute all this plethora of process where there, let me point out that we have 2 important couplings here, for instance, lambda 3 here, so an interaction of 3 dark matter particles, and lambda x here, which is basically the quartic coupling of dark matter. So these are like the 2 key couplings that we have to take care of. And now again, I'm showing you here the evolution of the comoving density of dark matter as a function, if you want, of the inverse of the time. So again, and this 3 to 2 is this yellow line corresponds to 3 to 2 process. So and again, the blue and the red correspond to semi-annihilation and the self-annihilations. So I just wanted to show you that even if the evolution is not exactly the same, it's pretty much the same. It's very close to the other one. So dark matter will decouple slightly later, but will reach the equilibrium, so this flat behavior, much earlier, right? And now, the point of this 3 to 2 annihilation, if these are the dominant ones, both direct and indirect detection are suppressed. Because after all, the dark matter is kind of decoupled from the standard model. So the annihilation will tend to produce dark matter particles, but not photons or antimatter or neutrinos. Okay, so we have computed this cross-section, the 3 to 2. Well, actually, if we compute all these cross-sections. And again, just want to emphasize that the couplings important here are lambda x and this capital Z, which is basically lambda 3 times the vacuum of the scalar Higgs, of the singlet Higgs, and divided by the mass. And here the parameter space that is allowed or that generates the 3 to 2 annihilations when they dominate. So first of all, so this Z, so basically lambda 3 and lambda x for 3 dark matter masses. So these 3 lines correspond to MeV dark matter, so 10 MeVs and 100 MeVs. And all this dashed line, or this dashed region, is excluded because of perturbative unitarity. So first point I have to point out is that we need dark matter mass in the scale of MeV. So if you have heavier dark matter, will violate perturbative unitarity. So first we need light dark matter, so MeV dark matter, and we need sizable couplings, so couplings of order 1 close to the perturbative unitarity bound. So I want to be very briefly because there's another observable that I want to point you out. So in lambda CDM cosmology, so lambda CDM is basically the paradigm for cold dark matter. So in this paradigm, it is lambda CDM cosmological model. You know that it has been remarkably successful in explaining cosmic structures over a huge range of redshift, but it has faced persistent challenge from observation that proved the innermost region of the dark matter halos and the properties of the Milky Way's dwarf galaxy satellites. So there are still some problems with the innermost, so the very small structures, and in a nutshell, with these small scale problems are divided basically in 3 regions, so in 3 categories. So one corresponds to the missing satellites, is that actually when you compute the results from n-body simulation and you compare them to what is observed, so it seems that there are much more satellites in simulations of the Milky Way galaxy than what is observed, right? So this is one point. Another is the famous cost versus score, is that typically dark matter and body simulations tend to favor profile with a spike, so with a cusp in the innermost region. However, this is not what is found in at least all the observations. All observations tend to favor more flat dark matter halos in the center. And there's another problem which is kind of subtle, which is called the too big to fail, and it's related to that the most massive subhalos in the simulations of these clumps seems to be too dense to observe, to host the brightest dwarf galaxies. So there are these small scale problems that could be solved. There are possible solutions. One is using the baryons, baryon physics. So because baryons are very difficult to simulate in n-body simulation. So we can have, for example, supernova feedback, or we can have a slow star formation efficiency, or we have a suppressed gas cooling efficiency as well. So this is one possible solution coming from more baryon physics, but there are also solutions coming from dark matter, and which is the one that I'm more interested in. So one option is to have, for example, warm dark matter, but I will concentrate in this option is from going from the collisionless paradigm of dark matter to self-interacting dark matter. So dark matter which has a sizable self-interactions. So this, okay, so observations of these previous problems coming from small structures, and also there are observations coming for instance, from the Bullet cluster, points out this self-interacting dark matter. So the elastic scattering dark matter cross section over the mass in a range of say few GeVs per gram. So in a range of say 0.1 to 10 centimeters square per gram, which correspond to a quite big cross section. So 10 to the minus 24 square centimeters per GeV or so. But remember that for the electroweak, typical cross sections are of the order of picobarn. So say orders of 10 to the minus 36 or so. So this seems to be very difficult to achieve with the usual WIMP, because there's a mismatch of say 10 orders of magnitude or so. If we want to have these cross sections, the cross section of this order, right? So when computing this cross section, the process that we actually have to compute is all this one. So the elastic scattering of dark matter mediated by a S or T channel of Higgs and rho. We can also have the contact interactions and all this. And again, the couplings that are most important here are, well, the key couplings are lambda 3, so the coupling between 3 dark matter particles, and lambda x, which is the quartic coupling, right? And now here I'm showing you the parameter space which is favored by the self-interacting dark matter. So again, it points out to the same range as I showed you previously. So the mass range, so MeV dark matter. So, and for example, this region corresponds to 10 MeVs, and this one to 100 of MeVs. And again, this dashed region corresponds to the region where perturbative unitarity is violated. So we want to avoid this region because we don't want to deal with non-perturbative effects. That doesn't mean that it's ruled out, just that we are avoiding this region. Okay, and again here, mass, I told you, has to be, the dark matter mass has to be light, so lighter than say 200, something like this, MeVs. Now I'm just showing you exactly the plot I just showed you in the slide before, and this is the plot corresponding to the 3 to 2. So it seems that the dark matter is generated by the 3 to 2 mechanism. It will also solve at the very same time the problems coming from small scale structures. So now I'm showing you a plot which all these points here fulfill at the same time. So, so let me say it again. All these plots, all these points here, blue and purple, are generated via the 3 to 2 mechanism, and they fulfill and they solve the small scale structures. So they have the good sigma over m cross section, right? So this is for two ranges. So the blue one corresponds to the sigma over m of between 0.1 and 1 centimeter square per gram, and the purple one corresponds to the range of 1 to 10 square centimeter per gram. So in two different parameter space. Here the mass, and here lambda x, and here I have the mass and z. So if you want lambda 3, right? So again, what you see here is that dark matter mass has to be in the MeV scale. So in particular, between say some dozens of MeVs till say a couple of hundreds of MeVs. Okay, and we choose just for giving a more precise idea of the parameter space that we have to use. So 3 benchmarks here, A, B, and C, that are described here. So as I told you, we need the masses. We have to be on the order of MeV scales. Coupling, at least we have to have one coupling which has to be kind of sizable. That we have these strongly interacting massive particles. And well, yes, there are just the details of the benchmark that we have chosen. And I think I'm running now out of time, so I can let you here with my conclusions. So what we have done is we have studied an extended scalar sector, and the stability of dark matter has been, it's guaranteed by the remnant Z3 that arises from the spontaneously broken U1. So we are spontaneously broken a global group, so we have a Goldstone boson that could be a candidate for dark radiation. So we have strong constraints coming from dark radiation, from the measurement of the number of effective degrees of freedom. This Goldstone boson as well plays a central role in the dark matter production and a central role in avoiding the heating up of the dark matter in the 3-2 annihilations. So there's a rich phenomenology that could be tested, for example, at the LHC when testing the Higgs properties, because after all, we have extended Higgs sector. I have presented you different thermal production. Maybe I forgot to emphasize that we are only caring about thermal production, so the self-annihilations and the semi-annihilation, which correspond to the WIMP, to the usual WIMP miracle, but also the 3-2 annihilation, which corresponds to the SIMP dark matter. So a different paradigm for the dark matter creation. And also we have at the end, for the SIMP dark matter, we have studied the self-interacting dark matter, which points out towards a MEV dark matter. And having this, is possible to solve at least 2 of these small-scale structure problems that I point you out. So that was basically all that I wanted to tell you guys. Thanks.
Thank you very much. Thank you very much, Nicolas, for this very nice seminar. And now we should go for the question round. Let me remind that you can ask questions to the speaker, to Nicolas, via Google Q&A at the webinar page, and also via Twitter with the hashtag LabOP. We have already few questions. Let me see. We have a question by Julio Pirueta. It is possible to extend. It is possible to extend the model. For example, use a ACU2 global chain charts also the standard model sector under it, break it with the extra dark matter sector into discrete symmetries, and recover a similar dark matter model, but also some kind of flavor model for the standard model.
So instead of starting with a U1, start with a SU2. I think in principle it's possible to do it. I don't see why not. Yeah, I don't see any problem with that.
Okay, we have another question from Roberto. I don't know what it's actually from Roberto or from people in Valencia. Say when semi-annihilation occurs, the standard model output particle should be a single.
Right, right. So in the vertex is 3 dark matter particles with the Higgs singlet, so with phi. And then this phi, after the symmetry breaking, it becomes a rho and an eta, so a Goldstone boson. But then you'll have a mixing with the Higgs. So you can also, at the end, you have semi-annihilation, you have a dark matter plus either Higgs or rho or eta.
Okay, we have another question by people in Valencia. The 3-2 process is exclusive of C3 symmetry, or you can try this by a non-abelian SUN group?
No, it's not exclusive of the Z3. However, Z3 is one option to have it, because at the end, what we want is an interaction between 5 dark matter particles. So, and if you want to have a renormalizable theory, so you need something like a Z3. Well, you can have like a Z5 if you want, but then it will be a non-renormalizable. So one option is to have a Z3, a Z4 will not do the job, a non-abelian SUN, it's also possible to have that, yes.
Okay, now we have a question by Jorge Diaz. What key experimental signatures should be looked for in order to either confirm or exclude this type of models?
Well, for when you have the WIMP scenario, you have like all the signatures that we are used to. For example, direct detection, indirect detection, and colliders. So that's clear. Maybe his point is about the SIMP scenario. So when you have the SIMP scenario, the point is that the main annihilation is this 3 to 2. So if the 3 to 2 is the dominant, I expect the dark matter, both the direct and indirect detection to be very suppressed. Because when you have, if the 3 to 2 is the dominant, you need the dark matter sector to be kind of decoupled from the standard model sector. So you need coupling that which have to be very small. So I expect both direct and indirect detection to be very suppressed. However, this small scale structure is like a cosmological test of these models and in general of dark matter. So I think that the one important point is that when you have dark matter, we have more than the typical three ways of testing. So indirect, direct, and colliders. But there also we can learn from cosmology, and this is important. And in particular in the SIMP scenario, so for strongly interacting massive particle, the cosmological proofs of dark matter are like a key point.
Okay, it seems that we don't have more questions.
We have a question here from Valencia, Herman.
Okay, we are taking a question from Valencia.
Yeah.
Go ahead, Roberto.
Okay, I have one question. It's about indirect detection. Let's say if you could have these 3 to 2 processes inside stars, but instead to have 3 dark matter and 2 dark matter, or maybe 2 standard model, you can exchange one of these 3 by 1 standard model. I mean, in the sense, in center of stars, we could have our density of dark matter. So maybe it's easier to have the coincidence of 3 particles at the same time to make the process possible.
So, Robert, if I understood your question, you want the 3 to 2, but in the initial state, you want 2 dark matter particles and, say, standard model 1 that annihilates into 2 dark matter particles?
Yeah, could be.
Yeah, but the point is...
And 1 dark matter at the end.
So, okay. So if you have 2 dark matter particles at the end, the problem is that this reaction will not change the dark matter number density. So because both at the beginning and at the end, you have 2 dark matter particles. So for the dark matter production, this will be, it will not enter, right?
Yeah.
If you want...
I meant you have 2 dark matter particles in the beginning plus 1 standard model, and the output is 1 dark matter particle plus 1 standard model. And
yes.
Have a kind of set 3.
But this seems to be, okay, this process has to compete with, for example, an elastic scattering, dark matter standard model into dark matter and standard model, right?
Mm-hmm.
The difference is that in your case, in the initial state you have 1 extra particle, so I expect this to be suppressed. Okay, in order to have the 3 to 2 annihilation to be the dominant, I mean, the price to pay is to have a very small couplings with the standard model, because otherwise the normal annihilation, 2 dark matters into 2 standard models, will be the dominant. So the self-annihilation or the semi-annihilation. So it's kind of tricky to have the 3 to 2 to be the dominant. So yes, I think the only option is to have a kind of secluded dark sector. So when doing that, kind of all the interaction with standard model are very, very suppressed. So I don't think this will be very useful. So the process that you are talking about, Roberto.
Yeah, thank Avelino. We have a question from Avelino.
Hi, Nicolas. Very good talk. Thank you.
Thanks.
So I have a curiosity. So what happens if instead of a global symmetry you consider a gauge symmetry? Because go ahead, sorry.
Yes, you can do the same thing. So the difference will be that at the end you will not have a Goldstone boson, but you will have like a Z prime if you want, right? If you start with a local group, in principle this could be done. The problem is that, as I told you, one of the things that we have to take care of is we want to avoid dark matter to heat up when the 3-to-2 annihilations take place. And here, this is guaranteed with the interaction, via the interaction with the Goldstone boson. So the Goldstone boson is the one that prevents dark matter to reheat. Okay, so if you get rid of the Goldstone boson, you have to find another way to keep the dark matter in kinetic equilibrium. But yeah, I think that in principle it's possible to do it as well. Start from a local group instead of a global one.
Thank you.
I have another question, Nicolas, to ask you. These bounds that you say that in your model dark matter has to be MEV scale, this is a generic feature of SIMP dark matter or just in this model?
SIMP and MEV, you say?
Yeah, to be MEV dark matter.
All the models I have seen, SIMP implies MEV dark matter.
Okay. Okay, I didn't.
Yeah, because actually, what you want, what this cosmological observation constraint is not the cross section, but it's the elastic cross section over the mass. So you have to, in order to increase this, you have to increase couplings. One option is to increase the cross section, and the other is to decrease the mass. So typically, you cannot increase infinitely the coupling because you have the perturbative that you want to keep, I guess. So it's good to take light dark matter.
Okay, thank you.
Okay, we have another question from Julio Virueta. He was want to ask first. And the question is about my previous question. Is there no problem in charging also the standard model sector? Could it possibly spoil the key property of protect dark matter from decay with the discrete symmetry?
But I think it's possible to start with a SU2 and break to a Z3. I'm not sure. Maybe it's a very nice answer. I think in principle it's possible to do it. I don't see why it's not. If you start with a SU2 and you break it down to a Z3, I think it will do the job. But I haven't think much about this option.
Okay, thank you very much. I don't know if we have more questions from Colombia, from Brazil. Well, if not, I guess we should thank the speaker again. Thank you very much, Nicolas, for this very nice talk. Have also very nice discussion. Okay, thank you. And we'll meet again in 2 weeks. Thank you very much, all of you, for following these seminars. Okay, thank you.
Thank you.